Hi, everyone. My name is Maddie.
And I'm Shane.
And our project is Obstacle Mapping Robotic Navigator and Materials Handler. And our advisor for this project is Dr. Kim. So just to go over the agenda for our short little talk today, we're going to do a project overview and then inform you on our current project status, as well as go over our schedule, tasks, and our budget.
As Maddie just said, we're going to start off with a quick overview. So this project is a proof of concept for a robot to map and navigate an area. A user will then identify some point on that produced map and some object we want to pick up. The robot will then navigate to that location on its own, identify and pick up that object. And in order to accomplish this, we're using the TurtleBot3 WafflePi, which includes the chassis, battery, LiDAR, and motors. So that picture there, those bottom 3 levels were what we got from the robotics lab at TCNJ.
So then just to comment on our project specifications. So we're planning to map and navigate a standard room of 11 by 12 feet. And then our mapping completion time should be accomplished within under 2 minutes. The object size that we're planning to pick up is 3 by 6 inches. And then the object weight is between 4 and 8 ounces. The time to identify an object is in 1 second per object. And then the lighting is typical standard room lighting at 500 lumens per meter squared. So next, we're going to walk you through our project plan. So just to give you a quick overview, we have our Gantt chart. So the first part of our project focused on research and design. And then the next part was development. Then we had fabrication and assembly, testing, and documentation. So now at this point, we're going to kind of take a deep dive into each of those sections and walk you through how we worked out all of those things through our project. So this is our current project status. So task 1 is research and design. So it was concept planning, parts research, system design, mechanical arm design, and retrieving the objects, designing the objects that were to be retrieved by our robot, as well as ordering parts.
So this is our system architecture. It was sort of our backbone for what we wanted to construct throughout the entire project. There's 2 main modules going on here. On the left is the station PC, which handles a lot of the calculations and major communication between our application and the robot itself. The other one, of course, is then the robot, which houses an NVIDIA Jetson Nano, which is our sort of mini computer that's going to handle the object identification portion of it. So as you can see there, there's some blocks breaking down different parts of it, but all of the pieces that are actually collecting the data start on the TurtleBot and are transferred over to the station PC. So alongside that, also on the TurtleBot is the circuit that drives things such as the arm, as well as we're including a ultrasonic distance sensor that's actually going to help us retrieve the object itself. The diagram for that circuit's on the left and the physical assembled one is on the right. And it's broken down into 4 major parts. There's the green box, which is the power converter, since our power source is 12 volts and everything we're using is running on 5 volts. So we have a quick little circuit to step that down. The red part is the stepper motor, which controls the rotation and actuation of the arm itself. So that includes a control chip as well as the motor itself. The blue part is the ultrasonic sensor that I just mentioned, which has a couple of resistors, and all of that is connected to the NVIDIA Jetson Nano through its GPIO ports. And here's a functional mock-up for the arm itself. So we started out just as like a picture of where we wanted the actuation to come from, and we actually consulted with Joe Zanetti, who runs the machine shop at TCNJ, and we came up with this design where we have a main arm that holds the entire thing, and then a lower portion on the bottom that actually pushes and pulls it. The pictures on the left, and a little sort of Lego mock design can be seen on the right.
So then we were able to arm in AutoCAD. So we kind of figured out all of the dimensions that we were going to need for the aluminum, as well as our different motor placements. So we have this top motor up here, which was for movement of pulling the arm back and forth. And then this bottom motor here, which was used to rotate the arm side to side.
So I'm going to take a brief second just to talk about ROS and Ubuntu, which is a major part that allowed the robot system to function in general. So ROS stands for Robot Operating System. It's a framework that helps you write robot software. It includes lots of tools, libraries, and conventions that help with this type of development. And it's also open source and is designed to work with different versions of Ubuntu, which is an operating system on a computer. And we're currently using version 18.04 with the melodic release of ROS.
And then for one of our last tasks in this first research and design phase, we have our retrievable object design. So we designed these objects to be able to be retrieved by our mechanical arm that we built. So we want it to be able to hook these blocks and be able to return them to the user. So next we have task 2. So this is going to be where we really start to develop some of our software and implement a lot of our tasks that we're planning on doing.
So the first thing I want to talk about is the room mapping, and that's powered by what's called this LiDAR sensor. This stands for light detection and ranging, and the specific one we're using is a 360 laser distance sensor, LDS01. The way that this works is beams of light are sent out periodically, and the environment will reflect these beams of light back into the sensor. And when it uses the time difference between sending the signal out and receiving it to find out the distance between the robot itself and whatever piece of environment that is. So you see there's that little animation on the right showing a sensor going around a room and actually seeing that object there. And these distances get compiled into the map that we're going to use. So next, talk about simulation. So this was a huge help in terms of development for a lot of the conceptual work, since there's a fairly big gap between what you've coded for something to work and it actually working on a real robot, because there's lots of different factors that are hard to take into account. And there's also the issue of we only have one robot, and Maddie and I needed to work on different portions of it simultaneously. So I set up a simulation environment in Gazebo, which allowed for parallel work to be done. So you can see there's a little model of the TurtleBot, and we're using this space here, and we wanted to map one major room in this house. And next I'm talking about autonomous navigation. So once the map is produced by driving around the TurtleBot, I wanted to make a way to have the robot navigate to some goal destination point. On the right, there is a picture of a map produced by the TurtleBot, which I'm going to talk about a little bit later. But on the left is an example of autonomous navigation. That red arrow on the bottom is the goal position and orientation. And the line between the robot and that point is its current path planned.
So now I'm going to kind of switch gears and talk about our object detection system that we kind of set up. So as you can see, these images, these are all images that were collected from around the lab, and it's of the different types of blocks that we're going to be retrieving. So a neural net was actually trained to be able to identify these different blocks. So 80% of the data was used for training the neural net, and then 20% of the data was used for testing that. So then for testing, we have the blocks placed in all different backgrounds so that we would be able to see how well our neural net was actually working. So in order to get this working, we used PyTorch, which is an open source machine learning framework. And we use this in combination with the YOLO V5 object detection algorithm. So when using these two together, we're able to feed the algorithm all of our data and then be able to test this algorithm by providing it with more data. And then we see that it was able to successfully identify the different blocks. So as you can see in some of these images, in this block, it identifies the block as red. And then in this image, it identifies the block as green. And we were able to do that with multiple images, as you can see. So then for task 3, this is our fabrication and assembly. So in terms of assembly, we were able to fully construct our mechanical arm in the machine shop. So we were able to cut out all of the aluminum and fully construct that arm. And the only thing left with that is we're planning on attaching a camera for the robot to be able to actually identify the objects in real time. And then we have our blocks, which are fully assembled, as well as the circuitry for the mechanical arm to be able to move back and forth and push and pull.
So our next task is, as I said earlier, testing, which includes mechanical arm accuracy testing, mapping and navigation, object retrieval, and overall system functionality. So I'm going to bring you through a few videos that actually demonstrate this functionality. This first one is mechanical arm movement and ultrasonic sensor. Hopefully it won't be too laggy, so you can see it's able to rotate in this direction and now actuate forward and backward. Now, I don't know if you can see it on the screen on the back, but I'm going to grab this block right here. The ultrasonic sensor is right under the arm, and it's able to detect the distance that I'm holding that block away from it. And this next one, this was a manual map of the robotics lab in Armstrong, which is our engineering building. So I've split it into a couple main areas. The blue is the robotics section of the combined lab space. The green box on the picture is the windows, which is where that picture on the bottom left is taken from. And the red is the Baxter robot. And so you can see it makes a pretty good representation of the space. And the last one is autonomous mapping in real time. So in this video on the left is the mapping portion of it. I know it's a little hard to see because I was working on two screens, but on the left, I'm currently placing down my points, which is going to dictate the area in which the robot will search. And now it is currently starting to search and map the space. As you see, that white map is filling in. On the right is the simulation space. And here is that room that we wanted to end up mapping, actually worked in simulation.
And then lastly, we have our documentation. So we have continuous documentation throughout the entire semesters, and then the mid-year report and final report.
So here's our budget. We were originally allotted $100 per student. So with the two of us, that's $200. But we did end up having to apply for a budget extension, which was thankfully approved. So now at this point, we are currently under budget.
And then just to go over our hours, so we estimated that we were going to spend at least 6 hours a week throughout the 2 semesters. So as you can see, we're just a little bit over that mark right now. And then just in summary, our main goal was to map an unknown space with our TurtleBot, and then be able to autonomously navigate to that space, identify a block using machine learning, and then develop a scheme to pick up our desired objects. Does anyone have any questions?
If no one has a question, I'll ask a question. You know, we heard from the other groups. Do you have any business ideas from this?
I mean, I think it could definitely be turned into something that could be used along the lines of a business. Our main goal was to do more of a proof of concept for like a hazardous navigation. So almost more like Department of Defense, like robot that's going to be able to go into some dangerous situation and then retrieve an object. But I guess this also could be used in some type of business. I'm just not sure exactly what the application would be.
Okay, I can see applications, but do you see any extensions upon? Because it sounds like you've pretty much achieved your goals.
So the final point that we're actually at is just the overall system functionality, because right now we have all of our different portions working on their own, but them melding with each other might cause some issues. However, we're very happy with where we're at, so hopefully it'll be not too difficult to get that final system all assembled in one piece.
In terms of also like improvement in this project, I could definitely see this project being taken on by another group of seniors to maybe make a more robust mechanical arm, or possibly make it be able to pick up a wide variety of objects. So I think that that is definitely how this project could be expanded upon in the future.
Are there other questions for this group?
So minor stuff for Shane. So you, this is pretty minor. So your power supply, I see you stepping down from 12 volt to 5 volt. So do you consider power dissipation around the linear IC that you employed? So do you
yes.
have, yeah.
There are actually some issues with that. So originally we were only using one of those, which ended up overheating and causing issues where our arm would no longer function. So what we actually did was split each of our components and give them their own dedicated like chip to drop down that 12 volts. And that was able to spread the power dissipation enough where there were no overheating issues.
Thank you.